Hi and welcome back to another lesson in the physics video series. Today we're going to be discussing the normal force and the coefficient of friction, and this is found in the reference tables, equation number 9. As you can see right here, it goes with the net force formula and the vector analysis we've been using thus far. Okay, let's get started. So far we've been using equation number 8, the F net formula, to determine the acceleration and the forces involved in moving a block. And here we have that block and the free body diagram of all the forces. Let's review it. The block itself is a mass. We make it a block because it is a convenient symmetrical shape. However, this mass, when multiplied by gravity, has a downward pulling force called the weight, which is equal to mass times gravity. Since the gravity is pulling down and this line here represents the surface and the block is not breaking through the surface like thin ice, something must be holding it up, and that's the normal force. In a moment we're going to discuss the relationship balance of static equilibrium between the upward and downward forces. Now, the applied force is the pulling force, F. I made it to the right in this diagram. And if there is friction, and now we will be discussing friction, it will be pointing to the left, which is opposed or opposite to the pulling force. Friction does not help the pulling force, but it works against it. Let's take a look at the F net equations for the vertical and then the horizontal axes. As you could see here on the left side, F net equals MAY. I used the Greek letter sigma. The sum of all forces on the y-axis is equal to the mass times the acceleration in the y-axis. Now we know that this equation has to account for all of the forces that are acting on the y-axis, and there are two of them, one pointing down, one pointing up. So the general formula is this: up minus down. Up forces are positive, down forces are negative. So we have the normal force minus the weight, up minus down, equals MA. But the A is 0. And why is the A 0? Because there is no acceleration in the vertical direction. As I said earlier, the block is not crashing through the surface like thin ice, nor is it rising like it's on an elevator. So therefore, the acceleration is 0. When the acceleration is 0, that makes the right side of this term 0, and then we add over the weight vector force, and we determine that the normal force equals the weight. So the F normal and the F weight are equal but opposite forces. That's Newton's third law. There's a rule you're going to learn. It's called the normal equals the weight when the surface is flat. And of course, later on, the surface will not be flat. But for now, when the surface is flat, we will use that rule. Now let's take a look at the right side of equations, which will describe the actions on the x-axis. So again, we start with the F net formula equals MA, except we're on the x-axis. The sum of all forces on the x-axis equals mass times acceleration on the x-axis. That's what these little subscripts x mean. We will use the sum of the forces formula, which breaks down to forces pointing right minus forces pointing left. Right minus left. All forces pointing to the right are positive. All forces pointing to the left are negative. And here we have the pulling force, which is the action force, minus the friction, which is the reaction force, equals mass times acceleration. This time, acceleration is not 0, because the pulling force, which is greater than the friction, causes this object to accelerate to the right. However, there's a special condition when you pull the object at a constant speed, and that's what it says here. When the speed is equal to an average speed, there is no acceleration. This is a special case when the pulling force will be equal and perfectly opposite to balance out the friction. Having the right term go to 0, giving us the pulling force being equal and opposite to the friction. The pulling force equals the friction at a constant speed. If the pulling force does not equal the friction, and it is greater, then you have an acceleration which is non-zero. Let's take a look in more detail at the force of friction. Using formula 9, F equals Greek letter M times the normal force Fn. This symbol, which looks like the letter U, is really a Greek lowercase letter m pronounced in the Erasmian tradition as mu or mu. The real pronunciation in Greek is mi. So here we could see in formula 9 on the reference tables the force of friction equals mu F normal. So we're going to solve for mu by itself and look at the ratio that it produces. When solving formula 9 for mu, from F equals mu normal, you get the ratio mu equals the force of friction divided by the normal force. Now, when the force of friction is equal to the pulling force, we have the letter F replacing the friction, because as we said above, in this special condition, when you're moving at a constant speed, you're just balancing out the friction with the pulling force. And of course, we proved that the weight and the normal are in fact equal and opposite to each other. The Greek letter mu in this special condition is equal to the pulling force to weight ratio. There are two kinds of friction: static friction and kinetic friction. Static friction is sticking friction, and that is given as mu sub s, and kinetic friction, which is dragging friction, is given as mu sub k. Let's take a look at the reference table and see how those are listed. At the bottom of page 1 on the physics reference table, you'll see this chart I have outlined in red, the approximate coefficients of friction. We use these with formula number 9. There are two columns, one for kinetic and one for static, and they are listed for several different materials. For example, rubber on concrete when it's dry, rubber on concrete when it's wet, rubber on asphalt when it's dry, rubber on asphalt when it's wet, etc. If you read a problem and they give you a material type, most often you are going to go to this reference table, look up the material type, see if it's wet or dry, see if the object is either moving, which is what kinetic means, or static, sticking, and you would use one of these numbers. The general rule is this: the higher the number, the greater the amount of friction. The lower the number, the less friction. So frictionless would have a 0 number. You could see that the lowest number on this chart is Teflon on Teflon, which is 0.04. Very smooth and slippery. Returning to this chart, we can see that the sticking and dragging coefficients can be analyzed and graphed out. We have a point at which, when we pull an object, it is locked by friction to the surface and it doesn't move even though we're pulling on it. That is the static friction sticking zone. But then, once it breaks free and we are able to drag it, the amount of kinetic friction required to keep it moving is much less than the static friction that held it in place. This diagram is broken into two sections. The dashed line that's right here is the boundary between the sticking or non-moving section, V0, A is 0, and the moving section, constant velocity, and still no acceleration. And this is the graph that represents it. So when you pull on an object and it doesn't move because the friction is holding it in place, it is sticking and you have a very high value of static friction. Once it breaks free, then a much lower value of kinetic friction is required to match the applied force to the friction. Let's take a look at a couple of problems to illustrate these points. In the following problem, an 8 Newton wooden block slides across a horizontal wooden floor at a constant velocity. What is the magnitude of the force of the kinetic friction between the block and the floor? So first of all, we know that the mass times gravity of the block is 8 newtons. We know that it's wood sliding on wood, and we know that it's moving at a constant velocity, which makes the applied force equal to the friction force. Let's take a look at the reference table and get the formula F equals mu n and find the value of the stickiness coefficient. So here we are on the first page of the physics reference table. Page 1, the approximate coefficients of friction, and we see that wood on wood has a value of 0.3 kinetic friction. So for kinetic friction, 0.3 will be used in the formula. And here's that value of 0.3 inserted for the red mu k. Mu k is 0.3 times the original 8 newtons gives you 2.4 newtons of kinetic friction. In the next problem, a 0.5 kilogram puck is sliding on a horizontal shuffleboard court and is slowed to rest by a frictional force of 1.2 newtons. What is the coefficient of kinetic friction between the puck and the surface of the shuffleboard court? You don't need to use the physics reference table, and they're asking for the coefficient of friction. So if they ask you for the coefficient of friction, you just need formula 9. F equals mu normal. And then you solve this, knowing that normal is equal to the weight mg. Solving for the mu k by itself equals the force divided by the weight. So the friction force, 1.2 newtons, divided by 0.5 kilograms times gravity. Sometimes they give you the mass of the puck. Sometimes they give you the weight of the puck. And this time they gave you the mass, so you had to multiply it by 9.8. And eventually you do the math and get mu equals 0.24. There are no units because newtons cancels with newtons below. So in summary, we see that there are two relationships. A horizontal relationship between pulling force and friction. They happen to be equal and opposite when you're moving at a constant speed. And a vertical relationship that shows that the normal force is equal to the weight when the surface is flat. I hope you enjoyed this video. Thank you for watching, and we'll see you in the next video.